we are going to discuss settings, draft, cleaning efficiency and production in the carding machine. We start with first settings. Setting means maintaining the right tolerance of space or closeness between two working organs of the machine, such as let us say Likarin to cylinder, cylinder to flat or cylinder to doffer. Incorrect settings affect the working efficiency of the machine, and it can also deteriorate the quality of the processed material. Therefore, settings are very important and crucial for the process. Now, setting depends upon many factors, some of which are listed here, which is fiber, that is whether it is cotton or synthetics, or whether it is man-made fibers like viscose rayon or polynoxic fibers, and it also depends upon the dimensions of the fiber, that is their length and fineness. It also is affected by the level of trash content in the case of cotton. So, quite a few factors are there which affect settings. Some typical settings are shown in the following table. These numbers indicates the distance between the two organs, and the unit is 1/1000 of an inch. This is what is generally practiced in the industry, and 1/1000th of an inch is normally known as thou in the industry. Let us look at the settings as shown, let us say between feed plate and Likarin. The setting is 10 to 12 thou. Between for viscose rayon, the same setting will be between 12 to 15 thou. For polyester, it will be 12 to 15 or maybe little more. For acrylic, it could be also little more. In the next table, the settings as well as the some comments about those settings have been shown. What we see here, the settings are basically very difficult to remember, but they are generally available. But there are few crucial settings which we must remember also. If we look the zone feed plate to Likarin, then we find that the setting is widened for synthetic fibers, being generally long to reduce the level of stress on the fibers. So, when we go from cotton to fibers like viscose rayon, polyester, acrylic, these fibers do not have any short fibers. So, on an average their lengths are more than the cotton, and therefore, when you want to switch over from cotton to processing viscose rayon or polyester or acrylic or such fibers, we have to widen the setting between the feed plate and the Likarin. Otherwise, the fibers are going to get damaged. The other setting is Likarin to cylinder, and generally this setting is fixed almost for all types of fiber. It is usually 7 thousandths, 7 thou, that is what is generally known as, and typically 4/1000 inch is 0.1 millimeter. Let us go to cylinder and flat settings. we can also see the values here, and we see that these settings are little more for synthetic fibers like polyester and acrylic. And why it is more? The setting is widened because these fibers are voluminous. So, we have to reduce the level of stress on them. The space is very narrow between cylinder and flat, the fibers are voluminous, and there is going to be a lot of abrasive stress which will be there on the fibers. So, we have to reduce the level of stress in order to protect the fiber from getting damaged. Also, the other possibilities which are there is the development of heat or temperatures. That also we have to avoid, because of the tremendous abrasive actions, that could be lot of heat generations, that also we have to avoid. And the other thing which may result is the formation of naps by these fibers. So, to avoid all such possibilities, we have to increase the settings when we try to process voluminous fibers like polyesters or acrylic or maybe nylon. Cylinder to Duffer settings is generally 4 to 5 thou, where the fibers are generally transferred. So, these settings, once it is fixed, it is not changed as we switch over from one fiber to another fiber. Backplate to cylinder settings is also shown here. If we look at these values, we see these values a little more, that basically indicates that entry to the plate is wider than the exit, and this is what is done practiced for all types of fiber. Entry point, the tufts which are coming a little more voluminous, and then they are made to pass through a narrow zone. So, that is how we set the plate. And the other thing which you can see is that there is a difference in the settings when you compare between cotton and the rest of the fibers. The reason is same, that the synthetic fibers are basically bulky in nature. Front plate to cylinder settings, you can also see that the entry to the plate is narrower than the exit end. Lacquering to combing segments, that is which are there below the lacquering, these settings are fairly constant. For cotton it is a little less, 16 at the entry point and 22 at the exit end, and rest are all same. So, these settings, one set is not changed unless there is a specific need. The other important setting is the undercasing of the cylinder from lacquering end to Duffer end. The values are shown here. The Duffer end is wider than the lacquering side, that is what we can observe, and this also because of the fibers being bulky in nature. There is another point that we can see, that for synthetic fibers the settings are little on the higher side, and not necessarily that is very high, but no, in this case it is almost constant, because this setting is not really very important setting, and hence once it is fixed it is really not changed from fiber to fiber. It really does not make much difference, since the settings are not so crucial from the processing point of view. Duffer to Duffer stripping roller, if we see the settings, it is 12 to 15 for cotton, around similar values for viscose rayon, for polyester acrylic little higher, and this is also because of the fact that these fibers are little bulky, especially polyester and acrylic. Viscose is not that bulky in comparison to cotton, but the proportion of short fibers which are there, it is very high in cotton, but it will be almost negligible in the case of viscose rayon or for polyester and acrylic. So, the differences that we observe in the setting is mainly because of the bulky nature of the fiber and mainly because of absence of shorter variety of fibers in the case of man-made fibers. These are typical values. So, the actual settings for a given situations may differ from it in the industry. Parameters that affect settings are fiber length, fiber fineness, type of fiber and production rate. How fiber length is going to affect setting? For a given fiber, if we go from shorter length to longer length, the most important setting that we need to change is the setting between feed plate to Likarin, because this is the point where a lot of force will be acting on the tufts which are being fed a relatively unopened state at this stage, and therefore, to avoid fiber damage we have to be very careful about the speeds and speeds of the Likarin and the setting between the feed plate and the Likarin. So, as the length is increased, we have to widen the setting, especially at this point, and we may also need to change the setting between cylinder and flat, because long fibers means lot of friction between the fibers and the teeth of the cylinder and flat, and there is chance that lot of frictional heat may be generated. At the same time, lot of force will be acting on the fibers, which may create naps, may generate or may lead to damage also, and hence the length is too long. We have to also adjust the setting between cylinder and flat. Next, go to fiber fineness. With finer fibers, cylinder flat setting becomes very crucial. This setting should be reduced in order to achieve thorough opening, so that the fiber clusters do not pass through. In the case of cotton, finer fibers are generally longer also, hence a widening of feed roller to Likarin setting also may be required. So, for cotton we not only need to adjust the setting between cylinder and flat, but also between Likarin and feed rollers, because long cotton fibers are also finer or vice versa, finer cotton fibers are also longer, and hence we need to adjust these two most important settings. The production rate can also affect setting. Generally, in high production curves, all the settings are slightly widened. However, the most important ones are feed plate to Likarin and cylinder to flat. These are the most crucial setting in the entire machine. Type of fibers, if we discuss, as I already mentioned, that man-made fibers are free from short fibers, like the short fibers we see in the case of cotton. The other thing is they are bulky and resilient in nature. There is a high fiber to metal friction between all synthetic fibers and metal. For polyester and acrylic, the cylinder flat and feed plate Likarin settings need to be widened in comparison to cotton, which we have already discussed, and the reasons also have been told. That the reasons are mentioned here: greater average length, absence of short fibers, bulky resilient nature of the fibers, and high fiber to metal friction. Because of all this, the stress level goes up when these fibers are teased by the Likarin or they are opened by the cylinder and flats in the carding zone. The other thing that may happen is that these synthetic fibers other than viscose are elastic in nature and will be more prone to nap formations when certain stress acts on them and the fiber gets released from the teeth of either the flat or the cylinder. The fibers will spring back and the internal energy of the fiber will cause the fiber to recoil, and while doing so it may take up some fibers from the neighbors and roll them in the form of naps. Therefore, this aspect we have to keep in mind while processing this synthetic fibers. The other thing is synthetic fibers are more prone to static generation. This is very serious. We all know that synthetic fibers, because they are generally hydrophobic in nature, they do not absorb any moisture. Moisture helps in dissipating your static charge, but these fibers do not absorb much moisture, and therefore, there is a chance a lot of static charge may generate. Though these fibers have some spin finish on them, but the spin finish may not be sufficient enough to take care of the static charge, and generally it has been seen that these fibers lead to generation of static electricity, and because of that they get stuck to the machine surface, to the metallic wire points, and do not get transferred easily from cylinder to topper. They do not want to get removed or stripped also from the topper surface. So, we face such problems. Hence, we have to think what to do to reduce the intensity of the rubbing actions. The rubbing action can also increase the temperature, also told earlier, and this temperature may go so high that the fibers may sometimes melt, especially thermoplastic fibers. Therefore, to reduce intensity of rubbing, to avoid fiber damage, nap generation, heat generation, what we can do is to reduce, or is to not to reduce, to widen the setting and to reduce the speed. That also is another alternative, or we can play with both, that we reduce the speeds of processing and also we can widen the setting, so that these fibers can be processed nicely. So, after discussing setting, now we go to draft. The draft is a measure of degree of attenuation, that is degree of reduction in weight per unit length of the material being processed. Draft in a way is stretch that we all generally understand. So, draft in this machine could be of two types, we call it mechanical draft and actual draft. Now, we will discuss what is mechanical draft and what is actual draft. Before that, let us see the drive of a carding machine. Today's carding machines are driven by number of motors. The typical gearing diagrams of a machine along with the motors are shown here. We can see there is a motor here, number 1, another motor there, another motor here, another motor here, another motor here. So, there are 5 motors which are driving these carding machines. In the old version of cars, that used to be only a single motor, but today's machines will always have multiple motors. Each motor takes care of one section of the card, so that the speed of these sections can be controlled independently and quickly from a central computer controlled controller. That is the purpose that we have quite a few motors. Now, if we look at this diagram, what we can see, let us say motor number 2. This is driving the feed part of the machine, which is from here to there. This part is the feed part. All these elements or organs are driven by motor number 2, which is here. Similarly, motor number 1 is driving liquor in, cylinder and flats. Motor number 3 is driving the delivery section of the machine along with doffer. Motor number 4 is driving, it is a fan which is sucking the dust laden air that the machine generates. The machine generate lots of dust because of this teasing action which is going on at different points of the machines. So, you exploit the opportunity to suck out the dust laden air in order to clean the cotton. In the case of processing synthetic fibers, dust is not there, and therefore, the sucking action may not be required or it is not so important. Now, let us discuss this draft, mechanical draft. What is mechanical draft? Mechanical draft is calculated based on speed of the machine elements. It is based on the speeds. So, we need to know the speeds of the different organs of the machines to find out the mechanical draft. So, mechanical draft is the surface speed of delivery roller divided by surface speed of the feed roller, or mechanical draft can also be length of sliver delivered per unit rotation of the delivery roller, length of lap fed per unit rotation of the delivery roller. Or mechanical draft could be length of sliver delivered per unit rotation of feed roller or length of lap fed per unit rotation of feed roller. So, this is the definition of draft, which is ratio of surface speed or length of sliver delivered and length of material fed for unit rotation of either delivery roller or feed roller. How draft can be determined? For mechanical draft determination, one needs to calculate the speed from the gearing diagram. So, if we have the gearing diagram of the machine with us, then we will be able to calculate or estimate the speed of the different parts of the machines, different rotating parts of the machines or moving parts of the machines. Otherwise, we have to use a tachometer to measure the speeds. The other thing is actual draft. Actual draft is the ratio of linear density of the lap and the linear density of the sliver. So, if we take the ratio of the linear density of the lap and linear density of the sliver, then the value that we get that is also known as actual draft. So, actual draft is not based on the gears or not based on measurement of speeds. Typically, draft of a carding machine varies between 80 to 100. That is the typically most of the machines can have these values of draft. In the machine, there are so many rotating elements, and therefore, one can find out the overall draft of the machine, or also one can find out the draft between two successive elements of the machines, because both are important for us. So, if the feed roller surface speed is represented by V f, taken by V t, cylinder by V c as shown in this table, then we can find out the draft between two successive elements by taking the ratio of surface speed as shown in column, fourth column. This is your fourth column, this is the third column, this is first column, this is second column, and this is the fifth column. In the fourth column, the ratios are shown. So, these ratios will give you the actual value of the draft in different zones. The fifth column is the name of the draft that we have given. Like the draft between cylinder and doffer is known as condensation draft, because here there is really no stretching of the material. On the contrary, there is going to be condensation of the material, which is coming from the cylinder side and falling on the doffer. So, here material from a large surface area of the cylinder is falling on a small surface area of the doffer, and therefore, there is going to be a condensation process, and we call it condensation draft. And the draft between doffer and wave stripping roller, calendar roller, collar calendar roller, these are known as tension drafts. So, these drafts in terms of their magnitude is very low, slightly more than 1, they are very close to 1, and therefore, they are known as tension drafts. The total draft is the multiplication of all these individual drafts. So, we have drafts V t by V a multiplied by V c by V t, V d by V c, V s by V d, V c r by V s, V c c by V c r. If we do this, then you see that these quantities they cancel each other, and we are left with V c c by V f. So, in the total draft, if we try to find out, then we need not to find out the individual drafts. We can find out the surface speed of the coiler calendar roller V c c, and we can find out the surface speed of the feed roller. Take the ratio of these two, that will give me total draft. That is how we can find out total draft, but if we are interested in the individual drafts, then we need to calculate the individual draft by taking the ratios as shown in the table. In this slide, some values of drafts are shown. Lap roller to feed roller. This is for an older version of card, where we are feeding the lap. So, there is a lap roller is there, and there is a feed roller which is feeding the lap to the liquor, and typical draft between lap and feed roller is 1.06. Between feed roller and liquor, it goes 1000, very high, because the surface speed of liquor is 1000 times more than the surface speed of the feed roller. Therefore, the lap that we are feeding or the mat of fibers that we feed, that gets stretched 1000 times. when it comes on the Lagrange surface. Then between Lagrange to cylinder the draft is 2, that means the cylinder surface speed is twice the surface speed of the Lagrange, and because of this surface speed differences, the tufts or the tuftlets which are there on the Lagrange surface, they get stripped easily by the teeth of the cylinder. So, here the draft is 2, cylinder to Doppler the draft is 0.04 because there is a condensation and the draft is less than 1. Doppler to calendar roller is around 1.1, calendar roller to Euler calendar roller is 1.05. So, in this case 1.06, 1.10, 1.05 these are the tension draft, and the cylinder to Doppler draft 0.04 we will call it condensation draft. Total draft, if we try to calculate, we have to multiply these individual drafts and we get a value 97.94, which is close to 98. So, for a typical machine, in the present case the draft could be close to 98. Actual draft, as we discussed little bit earlier, is based on the linear densities of the material fed and delivered. So, feed material is a lap or mat of fibers, or delivered material is a sliver. So, actual draft becomes the ratio of lab linear density divided by sliver linear density, both expressed in terms of kilotex. If we express in terms of indirect count, that is any, in that case actual draft is sliver count by lap count, or sliver count in terms of any and lap count in terms of also any. So, actual draft is weight per unit length of the lap divided by weight per unit length of the sliver. This is what we have to remember. The units may vary from text to any. Relation between actual and mechanical draft. In a steady state operation, amount fed per unit time should be equal to amount delivered per unit time in a machine. So, whatever we feed is same as to move out. Here the assumption is that the machine is not extracting any waste. So, for the time being, let us assume that the machine is not extracting any waste, and therefore, whatever we feed per unit time, that must move out from the machine per unit time. How much we feed per unit time? It is weight per unit length of the feed material multiplied by surface speed of the feed roller, and what we deliver per unit time is weight per unit length of the delivered material into surface speed of the delivery roller. Therefore, these two must be equal. From this relationship, we can say that weight per unit length fed divided by weight per unit length delivered should be equal to surface speed of delivery roller divided by surface speed of feed roller, whereas the left hand side now becomes by definition actual draft, and the right hand side becomes by definitions mechanical draft. Hence, actual draft should be equal to mechanical draft, ideally when the machine is not really generating any waste. But because of waste extraction, these two drafts will never be same. An actual draft will be mechanical draft into 100 by 100 minus waste percentage, as shown here. If we rewrite the equation in a different manner, we can write waste percentage is this, and therefore, it could be 100 into 1 minus mechanical draft by actual draft. A little mistakes in the spelling, please take care of it. Now, let us go to cleaning efficiency. Here is a diagram that indicates the combination of trash and lint in the input, in the output, and the waste percentage also shown. This is schematic diagram. Let x is the trash percentage in the input material, y is the percentage of waste collected, and z is the trash percentage in the output material. So, trash in the output with respect to input is going to be not z, z into 100 minus y by 100, and therefore, the cleaning efficiency will be the percentage of trash removed with respect to percentage of trash feed, and hence the formula is going to be this x minus z into 100 minus y by 100 divided by x into 100. This numerator defines the trash removed and x is the input. So, how much you have removed with respect to input expressed in percentage is basically cleaning efficiency. The waste percentage in the case of cotton varies between 4 to 6%. Hence, trash percentage in output with respect to input will change by a factor of 0.96 or 0.94. For all practical purposes, it may be considered close to 1, and in that case cleaning efficiency formula can be simplified. It is x minus z divided by x into 100. That becomes a simplified formula where we ignore the waste. Therefore, cleaning efficiency becomes trash in feed minus trash in delivery divided by trash percentage in feed into 100. Let us go to production calculation. Production means how much material is delivered per unit time. So, we need to know the delivery rate. For the delivery rate, if how to calculate delivery rate? It is speed of the coiler calendar roller, let us say is NC, the last rotating element of the machine which is delivering the sliver is the coiler calendar roller. Its diameter is let us say dcc. The hank of the sliver in indirect system is NE, that is what is mostly practiced in India, and let us say epsilon is the efficiency part. Since there is very little draft between Doffer and coiler calendar roller, the production for all practical purposes can be calculated from the Doffer speed also. This we must remember that in the industrial practice people calculate the production on the basis of Doffer speed. Otherwise, we can also calculate on the basis of coiler calendar roller or even calendar roller as well. It will not make much of a difference, since the draft between them is very little, they are all tension drafts. Therefore, production in kg per hour becomes Doffer surface speed, which is pi into Doffer speed into Doffer diameter in inch divided by this factor 36 into 840 multiplied by h, where h is the sliver hank, and if we want to include efficiency part, then this is the value which will come. If we multiply them, we will be able to find out the production per kg. The other concept which comes to our mind is production constant. Now, the formula of production calculation is given at the top. From this formula, now we have to find out what is production constant. In the calculation of production for a machine producing a sliver of given linear density and ignoring efficiency part, we see all the parameters in the above equation remains constant. So, here if we see that the parameter pi is constant, Doffer diameter is always constant, 36, 840 H for a given sliver is also constant. And if we for the time being we do not take care of the efficiency part, then we find out the production constant is basically pi into Doffer diameter divided by 36 into 840 into H. This value becomes a constant factor, and this is known as production constant. So, production therefore becomes production constant into Doffer speed. For ease of calculations in industrial practice, the production constant is determined in advance, and we can quickly calculate the production by multiplying the Doffer speed with the production constant. But obviously, the constant may change if the value of sliver hank, that is H, changes, that we have to remember. The next is selection of production rate. The practical production level of any car depends upon the characteristics of the raw material, the linear density of the sliver that we are going to produce, and the count and the quality of the yarn that we are going to produce. What sort of quality is required in the yarn? Accordingly, we have to choose the production rate. Typical production rates are shown in this table. What we see typically that broadly we can say when the fibers are shorter in length and they are coarse in nature, it is this value and this, the productions values could be high. So, short and coarse fibers can be processed at a faster rate, whereas fine and long fibers, you go to the lower values of the table, fibers are fine, the stable length is also more, the production rate has to be brought down. That means, short and coarse fibers is processed at a faster rate, long and fine fibers are to be processed at a slower rate. Why? Because long fine cotton needs to be processed at a slower rate than coarse and shorter cotton, as they are more prone to nap formations and rupture at high production levels. This is what we have to avoid, and therefore, we have to go for slower production rate when we try to process fine fiber. Fine fibers bending rigidity is very low, being very fine, and therefore, we have to ensure that they do not land up forming naps. Therefore, we have to reduce the level of productions. Generally, long and fine fibers are used to produce fine yarn count, and the sliver hank is also greater or more for finer variety of cotton. If we look at this, we can see that they are generally more. This is not kilotex, this would be hang value of the sliver. Production level for man-made fibers. Production levels for man-made fibers is lower than cotton, except for viscose or maybe for polynosic fibers. What are the reasons? The reasons are basically same as was discussed earlier. We have to see how these synthetic fibers are different from cotton. Synthetic fibers are prone to static charge formations. Interfiber cohesion is not strong enough to cause the wave to peel off easily on the Doffer surface. The wave breaks easily due to air current generated at high Doffer speeds. For the same length and fineness, viscose rayon and polynosic can be processed at a faster rate than other fibers, because they are not static prone. So, the main reason why we have to reduce speed is to avoid the generation of static, to avoid the development of heat, and therefore, production level has to be brought down, and that is what is all about the settings, the cleaning efficiency, the production and draft calculations of the carding machine. Thanks.